It's a pleasure to have with us Professor Sir John Hall, who will tell us about monodromy and work equilibrium for viscoelastic models with microstructure.
Okay, so thank you for the invitation here. And this is joint work with Capdeboscq. So Ina is the wife of Eve Capdeboscq, with whom I've already written a paper. So I'm going to find write a paper with my husband and my team. But Ina is a group theorist, actually, and also with Yasemin Şengül, who was my former student. Okay, so interesting. Okay, now we're going to okay, so many of you will be familiar with these elasticity models of solid phase transformations, where you have a functional that depends on the deformation of a material from some region in R3 to R3, so that's a vector Y, and the energy is a non-linear elasticity model. It's the energy density depends on the deformation gradient, which is the matrix and the cavity. And because the integrand is not in general quasi-convex, so it doesn't matter if you don't know what quasi-convexity is, but it's the central sort of convexity condition of multi-dimensional couplets of variations. It's essentially necessary and sufficient for the existence of minimizers lying along. And so in general, the minimum of this energy subject to suitable boundary conditions is not attained, and minimizing sequences generate infinitely fine microstructures as well. Minimizing sequence Yj becomes finer and finer, infinitely finer the limit as j goes to infinity. So there's one sort of picture of one nickel aluminum. So these are here you see two laminates in which the gradient alternates between two values, and then it needs another such laminate here. Of course, that's not infinitely fine, but it's very fine. And so in this model in which the energy of the interfaces themselves is ignored, the model predicts infinitely fine microstructures in the sense of minimizing sequences. So here's another famous picture. This is a high resolution picture, and you see the actual atoms, and you see a piecewise linear deformation, and the thicknesses of the interfaces alternate between 6 and 10 atomic spacing. So really incredibly fine microstructures. And actually, if you look, there are dots here. Each dot represents a column of atoms perpendicular to the screen. If you look very carefully at the dots, you see they look like this. And so you see that this is a result of a solid phase transformation. On one side of one of these interfaces, there's been this is face-centered cubic, and it stretches in this direction. And on the other side, it stretches in that direction. So that's how these interfaces are formed. That's not going to concern us today. Now, a major open question, or at least a major open question for me, is to describe this dynamically. So what we would like would be a well-posed model in which Y depended also on T, such that solutions of this model would generate such microstructures as T goes to infinity. So the dynamics would realize minimizing sequences. Now, little is known about this except in one dimension, when in the models that are being studied, that doesn't happen. And instead you have convergence to an equilibrium state. Unfortunately, I'm going to be in one dimension. I'll make a few comments just at the end, but so the issue is going to be whether you can prove convergence to an equilibrium state. Okay, so here's the model. Here's the equation. So if P is a function of X and T, X is in the unit interval. This is the time derivative, dp dt, plus the integral from 0 to 1 of sigma of E of S. So actually, you don't have to have 0, 1 here. You could replace it by any bounded open subset of Rn, and then you just replace this by the average over the subset of Rn, and that's actually completely equivalent to this problem. In other words, you can, without also generality, suppose that the open subset is 0. This is the equation which we're going to solve with initial data. So P0 of x, that's where time t equals 0. And the integral of P0 is going to be a positive constant mu. And so this equation, as I'll show, arises as the equation of motion of quasi-static viscoelasticity of rate type with hard, that is, displacement boundary conditions. It's studied in these papers here. So you see, it's a family of ordinary differential equations, essentially the same ordinary differential equation, except, well, for each x, it's p dot equals minus sigma of p, except you add on this average. So it's coupled by a single average. Well, that doesn't look too difficult, but it's actually quite tricky to analyze. Okay, so now how do we get the equation? So in one dimension, the equation of motion for viscoelasticity of rate type, taken for the density V1, is that the acceleration is equal to the divergence of the stress. So the stress here is split up into two pieces: a purely elastic part, stress depending on dy dx, the strain, plus a viscoelastic part where it depends also on y sub xt. So I'm going to choose S, the viscoelastic part, to be y sub xt, simplest possible case. And so then we get this equation. And now we're going to throw away the inertia term to make it quasi-static. Right, so now we have the equation here, d by dx and sigma plus y sub xt is 0, so we can integrate that, of course, and so we have the sigma. So if we have boundary conditions that at 0, y is 0, and at 1, it's equal to mu, then I can, this has got to be something that depends on t, and integrating it, you see that the function of t has to be this integral here, because the integral of y sub xt is y sub t between the endpoints, and y is constant at the endpoints, so it's 0, okay? So there's the equation. And now I'm going to let P be dy dx. Okay, so then you get the equation we had at the beginning. And the initial condition is P of x0 is P0 of x, and the integral of P0 of x is mu, because P0 stands for the x derivative, and the boundary conditions are 0 and mu. Okay, so that's where the equation comes from, and of course the integral of sigma, from the way the equation is derived, is a constant of motion, and so if you start with initial data with the integral of p0 being mu, then it implies that the integral of p will be mu for all t positive. And if we set w to be the indefinite integral of sigma, so that's the elastic stored energy, then we see that the time derivative of this is the integral of minus p sub t squared, so that the total energy, the integral of w of p, is a Lyapunov function. If this was constant, then p sub t would have to be 0, so you'd have to be at an equilibrium. So here are the hypotheses I'm going to make on W and sigma. So first one just says that it's a locally Lipschitz function defined on 0 infinity. So why do we want sigma to be defined on 0 infinity? Because sigma is a function of p is dy dx, and we want dy dx to be strictly positive to avoid penetration of matter. And so the second hypothesis is related to that. It says the stress goes to minus infinity if you try to crush it down to 0. Okay, so it's going to hopefully stop P becoming 0. And then the third one is perhaps the least intuitive, is that W is lambda convex. So if we add on a suitably large multiple of P squared to W, then W is going to become convex. And then the fourth one is a pair of conditions for large P and for small p. So the first one says that for large P, W is convex and sigma is increasing, so P big equal to 1 over epsilon, and it goes sufficiently fast to make this integral finite. And the second condition says that for small p, for p less than epsilon, W of P is strictly convex. Okay, so the hypotheses, and so H2, this one here, of course, implies that W of 0, the limit of WP exists, but it could be finite or it could be infinite. So, and then, well, the third one was perhaps the least intuitive, this lambda convexity, but in fact, the other three hypotheses imply H3. So those are the hypotheses. Those are things we assume. Now, what we don't assume is that W is convex. Equivalently, we don't assume that sigma is monotone. So that's a sort of typical sigma. So it's going to minus infinity as P goes to 0. It goes off to infinity sufficiently fast. It's got a few wiggles, right? Now, what about the equilibrium solutions? So the equilibrium solutions are that sigma has got to equal to its average. So sigma's got to be a constant. So the sigma has got to be a constant, but the integral of P has to be mu. Right? So now here's a value of C, here across here. So now you see that to solve sigma of P is equal to C, we have, in this case, 5 roots. P1 of C, P2 of C, P3 of C, P4 of C, P5 of C. And so what that means is that if I take, for example, a value of mu, which lies strictly between P5 and P1, then any function that takes these 5 values on different subsets of 0, 1, whose joint subsets of 0, 1, whose union is 0, 1, is going to give you an equilibrium solution. So there's a continuum of equilibria, and they represent phase mixtures. So each root, if you like, is a phase, and so you can arrange them anyhow you like, as long as the sets where you have where P is Pi, those sets, their union is 0, 1. So here's an existence theorem. So assume H1 to H3, then given P0 in L2 with P0 non-negative, so it could be 0, P0 in some places, but its integral has got to be mu, which is positive. Then there's a unique solution, which is a continuous function from 0 infinity to L2 of the equation. Right now, I haven't actually said carefully what a solution is, but there's a sort of obvious sort of definition of a solution, which is some kind of integrated version of this equation with initial data P0. And then, if in addition H4 holds, then there are universal upper and lower bounds for the solution. So that there are continuous functions epsilon of t and e of t, epsilon increasing and e decreasing, such that whatever the initial data is, p of x and t is bigger equal to epsilon of t and less than equal to e of t. And these are universal bounds for any solution, irrespective of the initial data. Or epsilon of 0 is minus infinity, e of 0 is plus infinity. So that's the existence theorem, and it's proved via, okay, so you can look for solutions. So this equation has solution. P is, when you split the interval 0, 1 into a finite number of disjoint intervals. And on each interval, P is going to be the same, right? So a given function of T on each interval. So it has exact solutions which are of that type for a given partition of 0, 1. So you have exact approximate solutions, if you like, for this problem. And then you use estimates from the Brace's theory of lambda convex gradient flows. This is in fact a gradient flow. Okay. Now, so what we're interested in is the asymptotic behavior of solutions. And so let's assume H1, H2, and H4, and then you have the energy equation. So the time derivative of the elastic energy is minus P sub T squared. P sub T is sigma minus the integral of sigma. And so it's easy to prove from this that P sub T tends to 0 in L2. This is P sub T. So it tends to 0 in L2 because its integral, okay, the integral is finite and the time derivative of it is bounded from the universal bounds. And so therefore this tends to 0. So that means if that's going to 0, that means that for large T, sigma of P of X and T is essentially like its average, right? So sigma P of X and T is like C of T for large T, and C of T is the average. So the question is, does P of X and T tend to some limit as T goes to infinity, for some equilibrium? And this follows quite easily if you can prove that C of T, which is the average, tends to a limit. However, to prove that C of T tends to a limit is far from obvious. What you do know is that the integral of C dot squared is finite. So maybe so this is C of T. So imagine you take the time derivative of that, you get sigma prime, which by the universal bounds is going to be finite, times P dot. And we know that P dot squared is integrable. So we know that the integral of C dot squared is finite. But to prove that C of T tends to the limit, you'd need that the L1 norm of C dot was finite. And so you don't have that, it seems. However, the good news is that you do know that positive orbits of solutions are relatively compact in L2. So this is a trick done by a trick due to maybe SAR. So you know that you can rearrange the initial data so that it's monotone, and then the solution stays monotone. And so then the total variation is bounded, and you can use Helios' theorem to extract a pointwise convergence subsequence, and therefore you get precompactness of the solution, relative compactness in L2. So that means that by the LaSalle invariance principle, if you know this, that the omega limit set of a solution is non-empty and it contains only equilibrium. Okay, so the issue is then, we've got a continuum of equilibria. We know that any solution approaches this continuum of equilibria. The issue is whether it stabilizes, or if it doesn't, then it would sort of creep very, very slowly around this continuum of equilibrium, getting closer and closer without ever stabilizing to a particular element of the set of equilibria. So that's the issue. So now it turns out that using a method of one of my first research students, Graham Andrews, and myself, you can prove stabilization under a non-degeneracy condition. So here is a version of the non-degeneracy condition. It's slightly different from the one in my paper with Şengül, but anyway, this is the one we're going to use. So sigma is going to be C1, and the measure of the set of critical points is 0, where S is P with sigma prime is 0. And if alpha beta, if alpha beta is a closed interval which doesn't intersect sigma of S, so it has no critical values, so no points where sigma is flat, then it will have then the equation sigma of P is equal to C will have an odd number of roots. It's got to go to the minus infinity. Sigma goes to minus infinity for small p and for plus infinity for large p. So it's got to cross an odd number of times. And so you look at the inverse functions. Pj of C of sigma of P is equal to C. Okay? And then you suppose that there's some constants lambda j which are not all 0, such that this linear combination, sum of lambda j pj, is constant as you vary C up and down in this interval alpha beta. So the non-degeneracy condition says that if that happens, then the lambda j's have all to be equal. But we'll understand this a bit more. Go on. So here's the picture then. So here I've drawn again with 5 roots, and here's C drawn with the red line. Okay. So you imagine C, and here's an interval alpha beta, you see, which doesn't contain any critical values. And we're imagining C going up and down in this interval, and of course the roots are going to change as you change C. And what we're interested in is whether you can have sum of lambda I pi of C being a constant as you vary C up and down in this interval. So the non-degeneracy condition says that, but if that's going to happen, then the lambda j's have all to be equal. Okay. And so here's a theorem, it's actually proved on paper here. So if H1, H2, H4 and the non-degeneracy condition hold, and there's an extra assumption here that for any interval alpha beta as previously described, the sum of Pj of C is not identically equal to 2k plus 1 mu. So the sum of C, where it's not equal to 2k plus 1 mu, right? Then the solution tends to an equilibrium P infinity in L2 as T goes to infinity. So I tried to give a very brief sketch of the proof here. So step 1, as I explained before, it's enough to show that the average tends to a limit as T goes to infinity. Well, if it doesn't, then there's going to be an interval alpha beta as described, which is crossed by C of T infinitely many times as T goes to infinity. And we can assume that this interval doesn't intersect the set of critical values, and you have a corresponding K. Okay, so that's step 1. And also as T goes to infinity, we've already remarked that P of X and T is like Pj of C of T. So that's the jth root corresponding to the value C of T on a set of measure mu j of T, and the sum of those measures tends to 1 as T goes to infinity. So we have, and now what we do is we multiply the equation by a function of the stress sigma. So you can do that by calculating the time derivative of the integral from some delta to P of F sigma. And so what we get is we think of the time derivative inside. So first of all, we Z is equal to P, so that gives you F of sigma of P, and then you have to multiply by P dot, which is sigma minus the integral of sigma. And then you rearrange it like this, and you see that if F prime is bigger equal to 0, then this whole expression is less than equal to 0, so that this limit exists. Well, that assumes that actually f is increasing, but if you choose f to be sigma plus epsilon g of sigma for small epsilon, you see that it implies that this holds for any smooth f. So you have a whole slew of functions here that are sort of expressed in a sort of awkward fashion, they're integrals of a function of sigma, whose limit exists as t goes to infinity. And you want to deduce from this that, in fact, that c of t tends to a limit. Okay. So now you use a detailed argument using step 2, and you have to use the non-degeneracy condition at some point. So I don't give this argument that you deduce that, in fact, if the mu j of t's, these are the measures where you're essentially equal to pj of t, they converge to mu j's. But then you can pass the limit, so you know that sum of uj of t, pj of c of t tends to is equal to mu, so you can pass to the limit, and you get the integral of you get a sum from j equals 1 to 2 kilograms. 1 of mu j pj of c is mu for all c in alpha beta. Right, and so and the sum of mu j's has to be the length of the interval. And so what we find is that we use the non-degeneracy condition, so the mu j's have all to be equal. But since some of them is 1, they have to equal 1 over 2k plus 1. And so then you get the sum of pj of c is 2k plus 1 mu, and the extra assumption in the theorem said that there is some c in alpha beta for which this is not true. So that's impossible. And so you get convergence to an equilibrium under the non-degeneracy condition. Well, the natural argument is the natural question is whether this non-degeneracy condition is necessary to prove the equilibrium. But perhaps there's convergence without assuming it, and unfortunately this is not known. That's an interesting question. So what is known? So Bob Pago proved convergence to an equilibrium for finite dimensional initial data of the type that I mentioned before. So you take initial data, you split 0, 1 into a finite number of disjoint measurable sets, and on each one, the initial data is a constant. And so it reduces the system to a finite set of ordinary differential equations. It's still not trivial to prove that solutions to that system converge, but they do so he proved it using a version of the Hale-Massat theorem. So that's one piece of evidence. Then there's this paper of Warhorse, Matana, Nguyen, and Weber. They consider a case when people have actually a C1 function on the whole of R, so it doesn't blow up as 0, and with sigma p having at most 3 roots. And then they show that there's convergence to an equilibrium if the P0 is in infinity, and the measure of sigma inverse of C is 0 for all C and R. Okay. So this talk is really about checking this non-degeneracy. If I give you a sigma, how do you know whether it satisfies this non-degeneracy condition or not? So then here's the condition. It says that the sum of lambda j pj is a constant for all c in alpha beta. For constants which are not all 0, then the lambda j are all equal. Well, is it true for a polynomial? Because a polynomial doesn't tend to minus infinity as p goes to 0, but it could be a polynomial for p bigger than epsilon, for example. So is it true for polynomials? Well, suppose you've got a polynomial sigma, which is p minus q1 minus q2, p minus qn, with real roots qi. So it's a real polynomial. So then, of course, the roots of sigma p is equal to c satisfy that by Newton's formula, the sum of the roots is just the coefficient an minus 1. So here we see there's a case where, as you vary c up and down, the sum of the roots stays the same. So in this case, of course, the lambda j are all equal to 1, and it's possible. You can have sum of pjc in the constant. It is balls. So here's a proposition. Suppose that n is a composite integer, so it's equal to the product of two composites, which is integers strictly bigger than 1, capital N and capital N. Then there's a real nth order polynomial and a non-empty open interval such that in that interval sigma has n real and distinct roots, p1 up to pn, and there are non-negative real constants mu j not all equal such that the sum of mu j pj is mu. So that shows that you have a problem. I mean, it's not a trivial thing to prove that the non-degeneracy condition is not true in general for polynomials. The proof of this is that you choose sigma to be the composition of two polynomials of order capital N and capital N, and then any root row of C of f of rho equals 3, corresponding to any such root, there are n roots pi of C of g of p equals rho of C, and the sum of those roots is constant, but it's not all the roots of the original polynomial. Okay. Now, monodromy. Of course, before working, I had the faintest idea what monodromy was. I've learned an awful lot of mathematics doing this, whatever the intrinsic interest of it is. Okay, so I'm going to explain what monodromy is in the context of a non-constant holomorphic function f from the Riemann sphere to itself. So the Riemann sphere is denoted by P1. Okay, so the Riemann sphere you can identify with the one-point compactification of the complex plane. So you add infinity to the complex plane, and it's done by stereographic projection. Okay, so now f is holomorphic. So of course you have to understand what a holomorphic function is from P1 to P1, and it's well known that such holomorphic functions are given by rational functions. So f of z is p of z over q of z for complex polynomials p and q. So that's a little bit confusing because, of course, q of z can be 0, in which case at that z f has a pole. But as a function from the sphere, Riemann sphere to itself, it's still holomorphic. It doesn't matter that it has a pole. It's just that a pole will get mapped to infinity. But it's still a holomorphic function. Okay, so now such an f, so a rational function, has a finite number of distinct critical points. So what's a critical point? So at the point at which f is not locally one-to-one, that means that in suitable local coordinates, f prime is 0. So of course, if c was actually infinity, then you'd have to choose proper coordinates around infinity, like 1 over z, for example. And so you have a finite number of distinct critical points, which are denoted C1 up to Cn. And the images of those critical points is the set R of critical values. And for any such f, the positive integer, which is the degree of f. So that means that for any p that is not a critical value, any p in the Riemann sphere, there's exactly n distinct inverse images of p under f. As long as you don't have a critical value, it has exactly n inverse images. Okay, so now let's fix picture first of all. So let's fix a P which is not a critical value. So here's the Riemann sphere, and these black dots are supposed to be the critical point. Okay? Now the images of the critical points are the crosses, they're the critical values. And I take a P that's not equal to a critical value. And I take, so it will have, this P will have n, because it's not a critical value and the degree is n, it will have n inverse images, Z1 up to Zn, they're distinct. Okay. So let's take one of them, say Zi of P. And what I'm going to do is I'm going to take a loop in the image here that starts and ends at P and doesn't go through any critical value. Okay. Now, so I'm going to look at a point at one of the roots, Zi of the starting point P, and you can show that there's a unique lifting of this curve starting at Zi of P. So that means f of the lifting is zeta I. So gamma is parameterized by 0 and 1. So gamma of 0 is gamma of 1 is P. And as you go around this curve here, and you start at Zi, there's a unique continuous map whose inverse image, starting at Zi, whose inverse image is gamma of T. Okay, and so you go like this, right? Now, what happens when you get to the end? Well, that means that this curve has gone back to P. All right. So what the end point is some inverse image of P, but not necessarily, of course, Zi of P. So that way, given this root Zi, you take this lifting, you get to another root, which I've denoted Z pi I. So that means that Zi of 1 is gamma 1 is P, so Zi of 1 is Z pi I of P, some pi of I, which is in 1 to n, and it's easily checked that this pi is a permutation. So it belongs to the symmetric group Sn. Okay, so you start at Zi, you get to Z pi I, and that's true for I equals 1 up to n. And so the set of such permutations forms the monodromy group of GF of P, which is a subgroup of Sn. So that's what the monodromy group is. And if you change the base point P, or the ordering of the roots at P, then you get essentially the same group. It's conjugate to the one you started with. All right, so that's the monodromy group. Okay, now it's well known that the monodromy group is transitive. So the permutation group is transitive if given any I and j in 1 to n, there's something in the group, in this case, the monodromy group, which takes I to j. In fact, you can see you can do that. You take a path joining Zi to Zj and avoiding critical points, and you look at its image, and that will give you a loop, of course, which begins and ends at P. And so that loop will give you a permutation that takes I to j. So it's a transitive. So the monodromy group is a transitive permutation group. Now, let's suppose that on some perhaps little continuous arc in P1 minus the critical values, the roots Zj, Zp is equal to P, that's P on this arc, they're finite, and that there are constants not all 0 with the sum of mu j Zj of P is equal to mu. Now, the Zj of P are locally homomorphic functions of P. Because this arc is not, it does not contain critical values. So by the function theory, the Zj of P are locally holomorphic in P. So that means that so if you take a P0 on this curve, then you know that the sequence of points P such that sum of mu j Zj of Pj is equal to mu, and Pj tends to P0. They're distinct points, right? So now, but this is a holomorphic function of P. And the identity theorem for holomorphic maps tells you that then that this relation would hold in some ball around P0. Okay? So if you have a holomorphic function which is 0 on the sequence of points that converges to another point, then it's identically 0 in that in a little neighborhood of that point. Okay. So now suppose you've got a closed loop and you have these liftings. And you look, so what I'm trying to show is that in fact, if I know that if I have a loop and I know at the beginning of the loop that this is true, then it's going to be true right the way around the loop. That's what can happen. Okay, so you take a closed loop, gamma of 0, gamma of 1 equals P0, with liftings satisfying J of 0 is Zj of P0, and you let S be the tor in 0, 1, such that the linear combination of Zj of T is mu for all T in 0 tor. And okay, so S is fairly clearly closed, and just by the argument that I just showed, that it certainly contains epsilon, positive epsilon. Now, if you take a tor in S which is strictly less than 1, then either gamma tor is P0, in which case the previous argument shows that you can go a little bit further and keep this linear combination for it's equal to mu. Or it's not equal to P0, but then when gamma of naught was P0 and gamma of tor is not P0, and so therefore there's going to be a sequence of times Tj less than tor with gamma of Tj minus gamma of tor less than 1 over j for large enough j, and therefore by the identity theorem, tor plus epsilon will belong to S for some epsilon bigger than 0. So in short, S is closed and it's also open, and so it has to be the whole of 0, 1. And so, in particular, you can put T is equal to 1. But at T equals 1, we know what zeta j is. It's Z of pi inverse of j. So you also will leave change variables to pi of j. So the sum of mu pi of j, Zj of P0 is equal to mu for any pi which is in the monodromy group. All right, now let's suppose that we know that the monodromy group is the whole of Sn. Okay. Well, that means that we could take pi to be a transposition that swaps I and j. So if I do that, so I know that, so I could take pi to be something that swaps I and j, and I subtract these two things. Okay, so everything's going to cancel except the ones corresponding to I and j. Right? And so therefore you get mu I minus mu j times zi of P0 minus j of P0 is 0, but the roots zi and P0 are distinct, and therefore mu I is equal to mu j. And therefore you get that all the mu i's are equal. Now, how do you know? How can you tell whether the monodromy group is Sn. Well, that you need to be a group theorist, of course, which is why I'm collaborating with a group theorist. So a simple sufficient condition is that all the critical values are distinct, and that at most one of them corresponds to a degenerate critical point. So that's because it's easy to check that the permutation corresponding to a loop around a critical value coming from a non-degenerate critical point is a transposition. So you somehow, it's just a little kind of calculation. And then, well, there could be one critical point which is degenerate. But in this case, we're working on the whole of the Riemann sphere, and so a loop around f of C star, where C star is a degenerate critical point, is generated by loops around the other points, because the sphere is simply connected, if you like. So therefore, under these hypotheses that the critical values are distinct, and that most one of them corresponds to a degenerate critical point, the monodromy group is generated by transpositions, and it's transitive. And a transitive permutation group that is generated by transpositions is the whole of Sn. This is no result. Okay, so now I show you a couple of examples where we actually explicitly check them. Here's the first one. Sigma of z is -1 over z plus p of z. P of z is a real polynomial of degree n bigger equal to 2. Its first coefficient is strictly positive. And then you check that this satisfies all the hypotheses of h1 to h4. So you can see that it goes to -infinity as z goes to 0, for example, and it goes to infinity as z goes to infinity along the real axis. And so to prove a convergence in equilibrium, you have to check the non-degeneracy condition. So what are the critical points of sigma? The finite ones, and that's why we differentiated. The finite ones satisfy the equation 1 plus z squared p prime of z equals 0. Now, naught is not a critical point, because naught of the pole is not a critical point, because if you change to 1 over z, you see it's not locally, and you see that it's locally invertible at 0, so it's not a critical point. And we suppose further that this polynomial has n plus 1 distinct non-zero roots, so that you can write it as, well, the first coefficient will have to be NaN from the form of this, and z minus z1 up to z minus zn plus 1. Now, so we're supposing that this polynomial has distinct roots. So therefore, as roots of this polynomial, they're not degenerate, right? Because they're distinct roots. So it follows that as critical quantities of sigma, the zi are non-degenerate. In fact, if you compute sigma double prime of zi, you see that you can write it like this, which is actually 1 over zi squared times 2z p prime of zi plus zi squared p double prime of zi, which is the statement that this is not the derivative, this is not 0. Now, the critical values might not be distinct, but generically they are, and you just add epsilon z to sigma, for example. So assuming this, you have that the monodromy group is the whole of Sn plus 1. And now, if you suppose that the sum of this is a constant for C and alpha beta for the non-zero constants lambda j, then if 2k plus 1 is strictly less than n plus 1, then you set lambda j equals 0 for j between 2k plus 2 and n plus 1. So then you'd have that this was a constant, but the lambda j have all to be equal, and some of them are 0. So they have all to be 0, but they're not allowed all to be 0 because they've got to add up to mu. So since the monodromy group Sn plus 1, the lambda are all equal, and 2k plus 1 is n plus 1, and that proves the non-degeneracy condition. So, okay, so sorry. But furthermore, if we know that the sum of the roots is equal to an minus 1 over an, because Newton's formula for the roots. And so you find that if an minus 1 over an is not equal to n plus 1 mu, that means that there's just one possible value of mu which you have to avoid, but if provided you avoid that one value, you get convergence to an equilibrium for this particular signal. So here's a second example, which is more tricky. Now we have log z plus p of z. Log z is the principal branch of the logarithm. Again, p is a polynomial of degree n to 2 with real coefficients. It again satisfies h1 to n. Well, in this case, it's interesting that w of 0 is finite, not infinite. So the stress goes to minus infinity, but w does not go to infinity. And in this case, you have that sigma takes u to P1 is holomorphic, where u is the complex plane minus the negative real axis. And so for this, you need a more general theory. And so there is a more general theory, which we developed, which follows the framework of Sakai. And it starts with, in this context, of maps from an open set u in P1 to P1. U is open and connected. You can also do it for general maps between room surfaces. And you define the cluster set, which are the boundary values of F. So they're the points in the image, which are the limits of F of Zj for Zj in U going to some boundary point. So that's a generalization of the boundary values of F. And it's closed and it's non-empty if the boundary view is non-empty. Okay. And then you let W be a connected component of the open set F of U minus the cluster set. Okay. And we assume that this open set is non-empty. In fact, it can be empty. It's a pathological example, but usually it will be non-empty. So you take a connected component of this open set, assumed to be non-empty, and then you look at the inverse image of that connected component, and you take a connected component of that inverse image. Okay, why do you do this? How does it involve procedure? Well, because then you find that F maps V to W, and the boundary of V to the boundary of W, and it's a proper map, i.e. the inverse images of compact sets are compact. And if it's a proper map, then general results tell you that it has a positive degree, so that for any W in W that is not a critical value, it has precisely degree of F inverse images. And so that means you can play the game with the monodromy group. You define it in exactly the same way as before. You lift loops in W with base point P that do not pass through a critical value to paths in V. Okay, so now returning to this example, sigma of Z is log Z plus P of Z. The critical points are the roots of this nth order polynomial. You could get 1 over Z plus D prime. So, and we'll assume that n is odd, and that 1 over Z P prime is this polynomial. It's a real polynomial, but it may have complex roots. One of them is real and negative, however, because if you look at log of minus t plus p of t on the negative real axis, you find it attains a maximum value. So here is some. So now the cluster set turns out to be these two lines, which end up at a point A, and with imaginary values minus I pi and plus I pi. Here's U. So actually, we're going to take W to be the complement of these two array lines, and sigma maps the positive real axis onto the real axis. So there is a connected component of sigma inverse of W that contains 0 infinity, and then sigma is proper. It has a finite degree D. And then you will see, as an example 1, to show that the maybe you have to add epsilon z to ensure that the critical values are distinct. And now there's another little argument that shows that if you take out in theorem 2, then if this sum is not constant on this interval, then the condition in theorem 2 holds, and we've got convergence to equilibrium. On the other hand, if it is constant, then you have the D has to be 2k plus 1, because you can add zeros and use the non-degeneracy condition. So you end up with these. But if you end up that this sum is some constant for, and you get a convergence, but if mu is not equal to that constant divided by D. Okay, at least we have then a couple of examples where you can explicitly check this condition. So we were led to discussing Blaschke products. I don't know whether you know what a Blaschke product is. Certainly, I never knew what a Blaschke product was, but they're very interesting things. Well, essentially, if you have a map from the disk to the disk that takes the boundary of the disk to the boundary of the disk, then it's a Blaschke product. And a Blaschke product is something like this. So it's an explicit form. And so in this kind of context, you can reduce the situation to Blaschke products. We have all sorts of results about, for example, the monodromy. So Blaschke products are very like polynomials, and it turns out that their monodromy group, the list of the possible monodromy groups, is the same as for the monodromy groups of polynomials. So, okay, so finally, a couple of remarks on what we'd really like to do. So for the 1D equation with inertia, so remember that I talked about this term. So it's original work with Andrews, and so Orpego essentially proved convergence to an equilibrium, but it was for mixed boundary conditions, which are much easier. So one end is fixed and the other end is stress-free. Much easier than the case with displacement boundary conditions. And now for the related equation, where you add a term minus y, then the corresponding energy now is the kinetic energy that comes from the YTT term plus the elastic energy, now plus half y squared that comes from this term. So for example, you could take y sub x to be the famous thing of half of y sub x squared minus 1 all squared. So that's a classic problem for which the minimum is not attained. Okay. So in fact, you can show that for this equation, which is a well-posed PDE, so the corresponding energy has minimizing sequences that generate infinitely fine microstructure as you get lower and lower energy. But it's the case that no solution of this one-dimensional PDE generates a minimizing sequence. So the situation is that, I think I'm correct in saying that the situation is that every solution converges to an equilibrium, and the whole phase space is I mean so the regions of attraction of all these equilibria fills out the whole phase space, and as you get lower and lower energy, there's more and more of these equilibria, but no solution actually produces a minimizing sequence. So there's a barrier in one dimension, some kind of obstruction for the dynamics to produce these minimizing sequences. Now, what happens if you go to 3D? So here's the sort of the corresponding, here we've got inertia, and now I've taken the simplest possible viscoelastic term minus Laplacian of y sub t. So existence and uniqueness of solutions is proved by Ribke and then Frieseker and Dulzmann, but there's no results on asymptotic behavior for this equation. There's some recent work of Komatos and co-workers on regularity uniqueness in 2D under weaker growth conditions than are used by Ribke and Frieseker and Dulzmann. It's quite interesting. It sort of gives the impression it's actually really a much harder equation than I imagined it was. So roughly speaking, this equation you can see why it might be easy to solve. So you can take this Laplacian of y sub t on the left-hand side, and you see you have a heat operator acting on y sub t is equal to this divergence. And then you invert the heat operator onto the divergence. And the heat operator is so good, it kills off any nasty stuff that is here. Now, numerical computations of Swart, 1991, suggest a mechanism by which minimizing sequences may be dynamically realized in higher dimensions. So he took a simple problem. He actually took, his energy was integral of ux squared minus 1 all squared plus u sub y squared, which has minimizing sequences which go to an infinitely fine laminate. So if you start initial data like this, then he ran the dynamics, and you see that he got the beginnings of new interfaces appearing between the old ones. So now it would be very good to rerun these simulations because now he was so much faster than we were in 1991. But he didn't get he got not much faster than these. But it would be very interesting to see actually what happens. So anybody who's got the energy to do that. But anyway, you see that there's a possible mechanism. But how you would sort of articulate this in terms of mathematics to prove that you could get infinite refinement for a given solution, I really don't know. Now, and then the last remark is that the model with linear damping is unfortunately not frame indifferent. So the correct condition for frame indifference is that the strength depends on dy sub t in the following way: dy times a symmetric matrix with a symmetric tensor, which depends on u. The u is the square root, is the right Cauchy green tensor, and its time derivative. But for this equation, it would be lovely to be able to prove that it was well posed under some conditions that allow you to have multiple equilibria. But it seems very difficult, and it seems that you can sort of get control on the u. The problem is getting some control on the rotation of the dy, and so okay. So anyway, that's the situation. We're very far from being able to do what we would like to do.